everyone, here we go. We are today talking about the June 2019 Combined Science Chemistry Paper 2 for the Foundation tier. Question 1 says, plants release oxygen into the atmosphere. What is the name of the process? What is the name of the process that releases oxygen to the atmosphere? Let's hope my pen's working. Now, is it combustion? Is it oxidation? Is it photosynthesis? Or is it polymerization? So, obviously, you've hopefully remembering from your biology lessons and a little bit of chemistry that it is indeed photosynthesis. Okay, combustion is when oxygen is used. Oxidation is when something takes in oxygen, and obviously polymerization is when small molecules join together to form one large one. Okay, it says, let me try and get all this on there. It says the atmosphere contains 21% oxygen. Figure 1 shows an incomplete bar chart of the main gases in the atmosphere. Complete the bar chart by showing the percentage of oxygen in the atmosphere. That is a typical question to miss. Don't miss it. You think there's nothing there to do. So you've got to draw a line here somewhere at 21. It doesn't matter how big the bar is. Okay, now it's going to be very difficult with my pen to draw it at 21 due to like how difficult it is to draw with this pen, but yeah, basically at around about 21. Do a better job than I did is all I'll say. But look, each is between 20 and 30. There are 5 little boxes, so each one must be 2. So it's somewhere between the 20 line and the 22 line is where your line should be. Mine could arguably be 22, and therefore I probably wouldn't get the mark there for my terrible drawing. Anyway, let's skim over that and move on. So it says calculate the volume of oxygen present. Calculate the volume of oxygen present in 300 centimeters cubed of air. Okay, now how would I do this? Very simply straightforward. You've got to say, okay, in 100 centimeters cubed of air, we've just done that, in 100 centimeters cubed of air, 100%, your percentage of air, there is 21, because 21% of the air is O2. Cm cubed O2. Therefore, to find out how much in 300, you simply do 21 times 3, and that gives you obviously a value of 63 centimeters cubed. Okay, an atom of an element has an atomic number and a mass number. Draw one straight line, good luck, from each of these numbers to the subatomic particles it shows to be present in an atom. So, the atomic number, what does it tell us? Does it tell us the number of protons, number of neutrons, total numbers of protons and neutrons, the total number of protons and neutrons, sorry, I read that wrong, that's protons and electrons, total number of protons and neutrons, or the total number of protons, neutrons, and electrons. Now, the atomic number tells us our number of protons. Also tells us the number of electrons in an atom, because those two things are the same. Our mass number is all the things with mass, and of the 3 subatomic particles, 2 of them have a mass of 1, and 1 of them have a mass of small, negligible, 1/1836. Okay, and the 2 that have a mass are the protons and the neutrons. There we go. Which test shows a gas is oxygen? So you should have done or seen these 4 gas tests. Okay, a few drops of lime water will turn cloudy when shaken with the gas. Well, that one is CO2. Okay, a glowing splint will relight. I'm just going to cross that because that one is for O2. Okay, a lit splint gives a pop. That's H2. And a piece of damp litmus paper will turn blue when placed in a gas. That's chlorine. It also bleaches it and turns it white at the end, or some alkaline gas. Now, the name given to group 7 in the periodic table. What is that? Okay, the name given to group 7 is the, let me try and write it, is the halogens. Okay, it's the halogens. The name given to group 0 in the periodic table is the noble gases. It's the noble gases. Okay, which of the following rows gives the colour of the group 7 elements, bromine and chlorine? Okay, now we've got to remember these colours. We need to remember these colours. Okay, So we've got chlorine is red-brown or yellow-green. Now, chlorine is yellow-green. Hopefully you remember that. Now, red-brown is actually bromine. Lovely. Okay. So the answer there is C. Okay. Now, figure 2 shows the melting and boiling points for bromine and iodine. There we go. Using the information from figure 2, what physical states are these things in at 50 degrees C? It's sometimes room temperature, but this is 50 degrees C. So at 50 degrees C, has bromine melted? Is -7 lower than 50? Yes, it is. So bromine will have melted from its solid form. However, will it have boiled at 50? No. Therefore, bromine is a liquid. Okay, so this one is a liquid at 50 degrees C. Now, melting point of 114. Will this have melted at 50? No. So this one is a solid. Okay, meaning the answer there is D. Brilliant. There we go, last page of this row. It says the densities of some group 0 elements shown below. Use the figure in figure 3 to suggest the density of krypton. Now you can see a trend of increasing here. Now you cannot accurately state what it is. However, you can reasonably assume that the number will be bigger than 1.4 but smaller than 3.5. So all you have to do is choose a number bigger than 1.4 but smaller than 1.5 and 3.5, sorry. So some number in between these two values, bigger than 1.4, smaller than 3.5. So let's just go with 2.3 because why not? Okay, and the answer is any number between 1.4 and 3.5, including 1.4 and 3.5, I might add. For many years, argon was used to fill filament light bulbs. That's a picture of a filament light bulb in case you can't remember what one looks like. When the bulb is in use, the metal filament becomes extremely hot. Explain why argon, rather than air, was used to fill filament light bulbs. Okay, now if the metal gets hot, it's going to react with things. Okay, because if you heat something up, they react more. Okay, so you need to remember that argon, being a group 0 element, a noble gas, is inert. It doesn't react. Okay, that's kind of what it does. So it doesn't react with filament. Okay, you might go the alternate route and say that in air, oxygen will react with the filament. That's absolutely fine as well. Oh, a blank page. It's one less page to do. Right, question 3. A student poured water into a beaker and measured the water's temperature. Look, there's a beaker and a picture of a beaker. The student added 1 gram of calcium chloride to the water and stirred the mixture and then recorded the temperature. Give the name of the apparatus that could be used to measure 1.00 grams of calcium chloride. That is, remember, we use the word balance in science, don't we? It's a balance. There we go. Now, the students' results were temperature at the start, temperature at the end. Explain these results using the type of heat energy change that occurs when calcium chloride dissolves in water. So, what has happened? It started at 21, it ended at 32. So it has increased, but by how much? You're shouting 11 at me, aren't you? It's increased by 11. This one goes to 11. Now, it is therefore, it's given out heat energy to the surroundings, and therefore it is exothermic. That is the kind of heat energy change that occurs. Right, calcium chloride is hazardous to health. Which hazard symbol could be expected to be seen on a container of calcium chloride? Okay, we've got some here, okay, some things. Now, this one, obviously, this one is flammable. So it's not that one, because that's not hazardous to health. Specifically, I mean, you could argue that being on fire is hazardous to your health, but it's not the exact symbol for it. This one is corrosive. Okay, so not specifically hazardous to health. Now these two are left. Now this one means it's very bad for local ecosystems. Basically, don't put it down the drain. That's what this one's saying. Therefore, the answer Therefore, left only is C, okay? Because these are bad for the environment. Let me write that in so it's there. Okay, these are bad for the environment. Okay, or hazardous to the environment, not hazardous to your health. Right, give one safety precaution students should take during the experiment. Okay, now, obviously, it's a reasonably safe experiment. I know sometimes we go a bit crazy with the whole safety, okay? Now, what you need to say here is safety goggles, okay? Now, don't write tie hair back because that only applies to flames. So if we're using a Bunsen burner, that is when your hair is tied back. Now, you guys in Dean Magna, your hair is always tied back anyway. But yeah, that is when hair gets tied back, is when there is a naked flame. Okay, that's really important for that. Here, to avoid getting the hazardous to health calcium chloride in your eye, you would wear goggles. Okay, you need to say goggles, specifically goggles, not safety clothing, not PPE, goggles. State one way the apparatus could be changed to reduce the amount of heat energy loss in the experiment. Now, obviously, this is just a glass beaker, so it will conduct the heat very well. So you could change the glass beaker. Now, you will remember, having done this, you did it in probably not in a glass beaker, although there maybe was a glass beaker present, but you did it, didn't you? You did it in a polystyrene cup. You did it in a polystyrene cup. Okay. Equally, you probably used a lid as well. So to stop the heat getting out the top, you had a lid, and to stop the heat conducted through the beaker, you use a polystyrene cup. Nice. Right. There are more pages on this than the higher paper. Right, the concentration of calcium chloride is 12 grams per decimeter cubed. Calculate the volume of this solution, okay, that contains 9 grams of calcium chloride. You must show you're working. Okay, so you've got your formula here. Okay, now this stems from C equals N over V. So you've ended up there with C equals mass. C equals mass, or N over C equals N over V. So what we need to use here is we need to rearrange that for V. So V actually equals M over C. Lovely. So we've got 9. 9 is our mass. We've got 9. Our concentration is 12. So it's 9 divided by 12. Use your calculator. Okay. And that gives you 0.75 decimeters cubed, because this is in decimeters. But it asks you for it in centimeters. This is why it's 3 marks, guys. It asks for it in centimeters cubed. Now, please note, you get 2 marks for this. 1 for that, 1 for this. And just to turn it into decimeters cubed, you just times that by 1,000 to get our final answer of 750. Okay, cheeky 3rd mark there. Next, oh look, a graph. Wow. Now this doesn't actually give us anything to do yet. There's no questions on here, as we can see. But look, it's a rates of reaction experiment. Magnesium reacting with dilute hydrochloric acid. And you've got a loss in mass on the y-axis there, and time in minutes. So you've got the loss in mass plotted against time. I have to come back to that in a minute because it's going to ask me to draw on the graph. I just know it. Right, name the apparatus that could be used to measure out 100 centimeters cubed of dilute hydrochloric acid. Okay, now you're not going to say beaker or conical flask. You're going to say a measuring cylinder, because that's what you use. You use a measuring cylinder. Okay, now explain why there's a loss in mass of the flask and the contents. Now, looking back at the picture, which of course you could do because it would be next to it, you would see the bubbles, okay, and you would see the bubbles, and that means there is gas being formed, okay. So in this case, it's hydrogen gas formed. Now, the tricky thing about gases is they don't stick around in the beaker to be weighed. They disappear off into the environment forever. So it escapes from the flask. The hydrogen escapes from the flask and therefore cannot be weighed. That cheeky gas. Now the graph shows the rate of reaction. slows as the reaction takes place, because it starts off steep and then slows down a bit. Explain in terms of particles why the rate of reaction between magnesium ribbon and dilute hydrochloric acid slows as the reaction takes place. Now this is a tricky question, okay? People always fall over on this because you've learned about the whole, hey, particles, they collide, etc. But what you've got to remember is as the reaction takes place, okay, so remember, we start off with reactants and they become products. That's our chemical reaction. Now, as our reaction takes place, these reactants turn into products. That means over time there are fewer reactant particles. There are fewer reactant particles. That looks like particles. There are fewer reactant particles. They're being used up. Okay? Now, if there are fewer reaction particles, there are fewer collisions. Okay, because there's less particles to collide, okay, and that means less frequent collisions. Because remember, when you talk about these collisions, you've got to talk about collisions per second, collisions per unit of time. You have. Now, next, the experiment was repeated using an acid of a higher temperature. All other conditions were kept the same. Okay, so after 2 minutes, what will happen? Now, if we look back at the graph, you will see that. Let's look back at the graph. If we look back at the graph, what's going on up to 2 minutes? Now, after 2 minutes, here, it hasn't finished. It hasn't finished yet. Now, obviously, if you don't change the mass of magnesium, the final line will be the same. The loss in mass will be the same, but it hasn't finished at 2 minutes. And what that means is, the mass loss will be greater over 2 minutes. Okay, the mass loss is greater over the first 2 minutes because it will react faster because it's hotter. Now, the original experiment was repeated using the same mass of magnesium powder. Okay, so instead of a piece of ribbon, you've got powder. Sketch on the graph the line you would expect. Now, here comes some more terrible drawing. Now, if you use powder instead of ribbon, what will go on? It will increase the rate of reaction. Okay, so more gas will be produced more quickly, and the rate of reaction will be faster. Now, so what we're going to see here, okay, is, excuse my terrible line, is this line will be steeper. Okay, as steep and as smooth curve as you can make it. Now, it's going to finish at the same point, okay? So the line should meet this one. Now, this is a terrible drawing of a line, but it will be steeper, okay, with a steeper gradient. Now, it has to be to the left of this line. Now, you can do it there. You can do it here. Anywhere to the left of the line is okay. I would suggest doing it nice and obviously in the middle rather than trying to hug it to the line too much so it's nice and clear. And make sure, and I'm going to write this on there, but you'll have to do it, that it finishes at the same height as the existing line. Finishes at the same height as the existing line. Okay, that's really important. Hard to draw with this pen I've got, but easy for you to sketch with a pencil. Okay, what's next? It says some reactions are affected by the presence of a catalyst. State the effect of a catalyst on a reaction. Well, it speeds up the reaction. Speeds up the reaction by lowering the activation energy. Okay, activation energy. Speeds up the reaction by lowering the activation energy. There we go. Devise a simple experiment to find out what happens to the mass of a solid catalyst during a reaction. Now, we know, hopefully, fingers crossed, that we know that the catalyst doesn't get used up. Therefore, the mass of the catalyst you put in should remain at the end. Okay, so we need to weigh a known mass of catalyst. You could state the mass if you like. Catalyst. Let the reaction happen. Let the reaction happen, then remove and filter catalyst. Hang on. So after reaction, remove and filter catalyst. Then weigh catalyst again. And obviously the start weight or the start mass should equal the end mass. And that will show that the catalyst hasn't been used up. Brilliant. Right, question 5. Most of the fuels used today are obtained from crude oil. Which statement about crude oil is correct? Crude oil is a compound of different hydrocarbons. Oh, it's not a compound. Okay, that would be one big thing. That would be crazy. So that was wrong. Crude oil is a mixture of hydrocarbons. That's correct. That one is correct. Crude oil is separated in several fractions by fractional distillation. 2 of these fractions are kerosene and diesel oil. State the use for each of these fractions. Now, hopefully, you've learned your uses of fractions. Okay, so kerosene is actually used as fuel for aircraft, and diesel is used as fuel for cars. Hopefully you've learned those. Now, it says kerosene is obtained higher up in the column than diesel oil. Kerosene and diesel oil fractions have slightly different properties. Choose a property and state how this property for kerosene compares with the property for diesel oil. Okay, so as you go up, for example, they get more flammable. So we will say flammability. And for kerosene, that will be higher, because as you go up, they get more flammable. Figure 9 shows the formula for a molecule of butane and a molecule of pentane. Butane and pentane are neighbouring members of the same homologous series. Explain why, using these formulas, the butane and pentane are neighbouring members of the same homologous series. Okay, all you've got to do is say that they have the same general formula. They're both alkanes. Okay, so they have the same general formula. Remember that CnH2n plus 2 thing we learned? They have the same general formula, okay, but they differ by CH2. So as you go up from butane to pentane, you've added a CH2, haven't you? That's a terrible drawing, but you've added a CH2 basically. The chain's got one longer and you've added 2 hydrogens, okay? Now, butane has the formula C4H10. Calculate the mass of carbon in 100 grams of butane, giving your answer to 3 significant figures. Now, the first thing you've got to do here is work out how much carbon in terms of atomic mass there is in there. So, there's 4. Let's write this bigger. So, it's C4H10, okay? You can see it up there. So, that means there's 4 times 12 carbons, which is, as we know, 48. Okay, now that means 48 of 58 is carbon. It does. And that means then if you take that and times it by 100, you end up with your final value of 82.8 grams. Fantastic. Okay. Now it says to give your answer to 3 significant figures, hence I have, you'll note your final answer from this would not be to 3 significant figures. My calculator says 82.759. You've got to do it to 3 significant figures. Butane burns completely in air to form carbon dioxide and water. Write a word equation for this reaction. Now, what that means is, and I'm going to have to try and squeeze this in as best I can, butane plus oxygen. Okay, because it tells you that butane burns in air, and you should hopefully know that the oxygen is the part of the air that participates in combustion. And then it tells you the 2 products there. All you've got to do is write them down. Okay, carbon dioxide plus water. I'm not going to fit it on, so I'm going to write it like this. Carbon dioxide plus water. Okay, it tells you the 2. Such a generous 2 marks there. All you have to know is that oxygen is the part of air that participates in this reaction. That's all you have to know. The rest of it they give you. It's very generous of them. Ooh, we're at the end of the line. Now, this is the last row of stuff because there's the periodic table and there's a big long write question. Anyway, oh, and a blank page. Blimey, right. Let's go. There's nothing else there, is there? No. I have to use the whiteboard software to do this so I can write on it. I tried Adobe, but it didn't work. Anyway, let's go and let's think about an aluminium atom. Okay, so the one on the periodic table has an atomic number of 13 and a mass number of 27. Which row shows the number of subatomic particles present in an aluminium ion? Al3+, so it's lost 3 electrons. Now, if it has an atomic number of 13, that means it has 13 protons, so it's A or B. Okay? Now, it should, as the atom, have 13 protons and 13 electrons. A is the aluminium atom, but it doesn't ask you for that. It asks you for the 3+ ion, which has lost 3 electrons. So it is, in fact, B. These two are wrong because with an atomic number of 14, they're not aluminium. Magnesium burns in excess oxygen to form magnesium oxide. The balanced equation for this reaction is this. Start with 1.35 grams magnesium. Calculate the maximum mass of magnesium oxide that could be formed in this reaction. Now, this is one of those funny moles questions. There's funny questions where you may have been given various ways to do it. Okay. Now, there are various mathematical ways to work through doing this. Okay, so let's look at one of them now. So you need to know the MR of MgO is 40. It's 24 plus 16, that equals 40. Okay, so the MO of MgO is 40. Okay, so that means that 1 gram of magnesium will make 40 over 24 MgO. Okay, which equals, based on my calculator here, 1.67 G of MgO. Okay, so 1 gram makes 1.67. However, you haven't got 1 gram, you've got 1.35 grams. You just need to scale that up. And to do that, okay, you just need to write that. Essentially, you'll end up with 40 times 1.35 over 24. That gives you your final answer of 2.25 grams. Okay, so that's just one of the ways you could do it. Now, if you know another way, if you've seen another way, if you were taught a different way that gets you the answer of 2.25 grams, go for it. Use your way, the way that works for you. Okay, you'll note if you've watched the higher tier one, that's a different way to the other way I did it on the higher tier, because this question's on the higher tier paper. You'll notice I did it a different way on the higher tier paper. Okay, there are many different ways mathematically, and as long as you get the right answer, it doesn't matter which one you use. So use the one that works for you. If you go away and find another way to do it that you like, use that one. Good stuff. Now, next one says, chlorine reacts with hydrogen to form hydrogen chloride. Write a balanced equation for this reaction. Ooh, brutal. So, chlorine, Cl2, reacts with H2 to form HCl. It does. Now, we need to balance this, so let's go with that. So you've got 2 chlorines, and you've got 1 chlorine. Let's put a big 2 times that. Yeah, I mean, now you've got 2 chlorines. How many hydrogens now? How many? There are 2. And you've got 2 on that side. We're done. That's it. There we go. Much easier than the ones I did with you in class, isn't it? Anyway, let's carry on. So, now the last one, right? Sodium chloride is like, this is your big 6 mark long extended answer one. Sodium chloride is an ionic compound containing sodium ions, Na+, and chloride ions. Figure 10 shows the electronic configuration of sodium and chlorine atoms. Okay, so those are the atoms, the elements themselves, not the ions, the atoms. Explain how sodium and chlorine atoms form the ions in sodium chloride and how the ions are arranged in the solid sodium chloride. Okay, so you've got to first of all talk about how these things form ions. Now, you should know, hopefully, that sodium, with 1 in the outer shell, is trying to get a full outer shell configuration. Is it going to lose 1? Is it going to gain 7? Well, it's going to lose 1, isn't it? It's going to lose 1 electron. Okay? 1. Write 1. Please write 1. Do not write an. No. Write 1. It loses 1 electron. Say the number. Sometimes it's going to do more than 1. Okay? You've got to state the number. Sodium loses 1 electron. It does. Okay? That means the configuration of the ion is 2.8. Okay, so it's lost 1 electron. Now, that electron is transferred to chlorine. Let's write Cl. Chlorine gains 1. Again, no an. Don't write an. 1 electron. Chlorine gains 1 electron. And the configuration of that is 2.8.8. Okay? Now, ions are attracted due to opposite charge Now, if you want to be really fancy, what you're going to write here is electrostatic attraction. I'm getting too excited here and writing too quickly. There's 2 O's. Electrostatic attraction. Okay, which is a fancy way of saying that opposite charges attract. You're going to be really fancy there and say electrostatic attraction. So they're attracted due to opposite charge. Now obviously there's a plus and a plus 1 and a minus 1, which means there'll be a 1-to-1 ratio of ions. And in that special word starts with an L, in a lattice. Okay. And what that means is, I'll draw it up here, you're going to have an Na plus ion surrounded by Cl minus ions. Now obviously I can't draw, you've got to remember there'd be 1 in front of this and 1 behind it as well, and of course each Cl minus ion is also surrounded by Na plus ions, and so on and so forth. I could draw this forever, but I'm not going to. Okay, basically that's what's going on there. It's a lattice, okay, with a 1-to-1 ratio of ions. So basically every time there's a chlorine, there's a sodium. You know, there we are. Now there we go. Fantastic. So I hope this has been helpful to you. I hope you've enjoyed, and feel free to watch some more. Thank you very much, and good luck.